A very good morning to one and all. Very good afternoon to one and all. It's honor to introduce today's chief guest, Dr. N. Varadarajan, postdoctoral research fellow at Oslo University Hospital, Norway. He has completed MSc Mathematics in St. Joseph College in Trichy, MPhil Mathematics in RKM Vivekananda College, Mylapore, PhD in IIT Kanpur in the year of 2018. Our research person having more than 10 years of teaching experience in engineering college. He visited Dalhousie University in the year of 2015, Canada, and University of Illinois Urbana, USA in the year of 2017 for research. Currently, he is engaged in research on medical field CT, MRI, echo, heart images using deep learning based segmentation and its application on the augmented or virtual reality visualization and everyday clinical uses. I welcome you, sir.
Yes, thank you, madam. Am I audible?
Audible, sir, audible.
Okay. Thank you for this great introduction and good afternoon to all. I'm going to talk about spectral stability of some nonlinear waves and our wave solutions. Today is 12th, I think, and it was compiled yesterday, so that's why it's showing 11th. So the overview of the talk is introduction. I will introduce what is like some behaviors of solutions, differential equation solutions, and some what is nonlinear differential equation, then spectral stability and linear stability and stability, nonlinear stability, everything in the second part. Then I will show a use case or a test case in the third part. That's my plan. Is it audible again? I'm asking you because.
Audible, sir. Audible. No problem,
okay,
sir.
Okay. Thank you. So here I shown some differential equations. So the first one is ordinary differential equation with the constant coefficients of second order. I think you are familiar with this. It's a, I think, school level problem. So in this, the coefficients are constants and the order is 2. The second term 4dy or dy by dx is related to damping of the system, because we are teaching many like this kind of equations, but the first order is related to damping or velocity, related to velocity in terms of physical applications. The right hand side minus 2 cos hx is known as forcing function. So this is how people are getting force for a system. Basically, this differential or any differential equation, this is from a physical problem. It's not like we are taking d square y by dx square or dy by dx like that. It represents a physical system. So that we need to keep in our mind. So the system represented by the left hand side is getting force, continuous force from the right hand side function. That's the meaning of this equation. Then the solution of this differential equation is the second one, y equal to e power minus 2x c1 cos x plus c2 sin x minus e power x by 10 plus e power minus x by 2. So if you see here, there are 3 terms. In particular integral, there is a term, and in the left hand, the first 2 parts are from complementary functions. So if you take first part of this solution, c e power minus 2x cos x and a constant c1, that itself satisfies this differential equation. The second part as well, c2 e power minus 2x sin x also satisfies this equation. This behavior is only in you can use it in only in linear differential equation. If you see a nonlinear differential equation, then if you have solutions f1 of x, f2 of x, or f3 of x, like 3 solutions, in the nonlinear differential equation, the linear combination of this c1 f1, c2 f2 plus c3 f3 is not a solution. But in the linear case, it says again the linear combination is also a solution to the given differential equation. That's the important point. That's one of the important point between linear and nonlinear differential equations. The third one is the figure represents e power minus x sin x. So e power minus x related to the decay of the system, because x tends to plus infinity. So e power minus infinity, that tends to 0. Then sine is always, sine or cos is related to oscillatory motion. So even though if it is oscillatory, this e power minus x drags this solution to 0. When x tends to plus infinity, then this e power minus x sine x is then 0. That's why it's oscillatory and decaying solution. Then the second row, first figure of the second row shows or represents e power plus x sine x. So e power, if x tends to plus infinity, e power x is e power infinity. E power infinity, you know the value. So then it represents the growing solution. It's oscillatory and growing. So e power x is reason to the growth, and sin x is always oscillatory. It shows oscillatory motion. Then the figure 2 and 3 in the second row are some other examples for oscillatory decay and oscillatory growing. So the second figure in the second row is oscillatory decaying, and the third figure in the second row is oscillatory growing. So these are examples. Then, so what is nonlinear differential equation? So a differential equation, and it's not linear in the unknown function and its derivative. That's called a nonlinear differential equation. For example, in the first equation, it's a second order. This 2, 3 represents the order of the differential equation. It's taken from Wikipedia. You can also find it. So it's a second order in R. So the derivative, the highest derivative is 2. Then R, the first term shows the nonlinearity. So R is a dependent variable, unknown function. R and d square R by dt square. This shows nonlinear behavior for this solution. So other terms, so the second term, dr by dt whole square. So that also leads to that. In the second equation, you have in the second equation, it's a third order differential equation. It's an ordinary differential equation, and the second term is related to nonlinear. So y and the d square y by dx square are taking to the nonlinear behavior in this case. Then we will move to some wave solution. So these are also taken from Wikipedia, and here in the first figure, there are waves moving from the droplets, and it's going to the until very long distance. Then it decays. And figure 2 and figure 3 are also nonlinear waves. It's taken from ocean. So it doesn't change the shape while traveling. That's the definition for traveling waves, or in case of traveling waves. The application in when you define nonlinear PDE, so we are moving to some simple case to PDE and nonlinear PDE. Nonlinear PDE, you have application in many fields, almost in everywhere. If you have more than one independent variable, for example, time and spatial value, then you can represent that system is by nonlinear difference PDE, partial differential equation. The application in almost in every field. So then we will define types of solutions. When you say traveling wave, the wave maintains shape while traveling with a constant speed. And then we can define stationary wave. Stationary wave depend on the observer. So if observer and and the wave is both are moving in the same speed, the observer doesn't feel the motion of the wave. For example, when you are sitting in a train and there is a car traveling parallel to you, and you are both traveling the same speed, then you don't feel that the car is moving or train is moving. That's the here example for stationary. Then periodic wave, right? Sine and cos are oscillatory, so these are periodic. Front, pulse, etc. These are some special cases of waves. So in this figure, the first figure shows pulse solution because the shape is like a hump. Then in the second and third, so you have one steady state in the left side and the other steady state in the right side. So this leads to front and pulse solution. Suppose you are representing a solution u of x comma t, then for a differential equation, then you can relate x and t by a single variable, xi. Xi is x minus ct. C is the wave speed, x is the spatial variable, and t is the temporal variable. Or you can have more other variable as well, like t or y, or you can have more than one says spatial variable as well in this system or in this type, in this side. Then based on C, we can classify these waves, these solutions. So when you combine x and t in psi with psi, then xi is x minus t. Then you can write u of x comma t as u of xi. If C is not 0, then it's a traveling wave. Suppose if you take C is 0, then u of xi is called stationary wave. Then there is other variable with other value with xi is suppose L. U of xi plus L is u of xi for all xi. It's simple like sin x. Sin x plus some value is again you can write oscillatory. So the same is represented in the periodic case. And the other one is front. Front is when xi tends to plus infinity, the solution u of xi is represented as u plus. When xi tends to minus infinity, then u of xi is called here u minus. Then u plus not equal to u minus, then it's called front solution. So in front itself, there are two like front and back. There are generally you can say front, but there are two kind of solutions in the front case itself. Then if u plus equal to u minus, both steady states are equal, then it's called pulse solution. So this case, you can see if you take a particular ring, then both ends in the spatial value are same, but see a dentist caliper in your then in the second and third, you have two steady states. In the third figure, for example, it's showing lower value for u minus, and the higher value in the right hand side is u plus. You can take it that way. The application for wave solution is in many fields, in mathematical biology, water waves, nonlinear optics, and so many you can say examples also. But it's not easy to solve these nonlinear PDEs, but there are some methods to solve these nonlinear partial differential equation. For example, backline transform, Hirota bilinear operators, Painleaf expansion, and etc. There are other methods as well. Now we will, I think you have now idea about what is linear and nonlinear differential equation, and when you can define PDE, and what are the types of wave solutions, and how you can distinguish this. I think you have some idea. And suppose you have a solution, this solution, for example, u of xi is c not equal to 0, or u of xi c equal to 0, or periodic wave, or front, or pulse. Then my interest in this talk is on stability analysis, particularly spectral stability analysis. So I will explain what is spectral stability, linear and nonlinear stability. Nonlinear stability is the like a big umbrella. Then these others are like small domains under nonlinear stability. If you say spectrally stable, you cannot say linearly stable. And then if it is a system is linearly stable, you cannot like defend yourself. It's a non-linearly stable. Linear spectral based on eigenvalue.
Are you already in the meeting?
Yeah. So yeah, I'm back now. So spectral stability is a very like a low like level configuration. Then you have linear and then nonlinear stability. For example, if you have a solution, if you have a differential equation PDE, ut equal to f of u is a nonlinear partial differential equation, and with initial conditions u of x comma 0. When time equal to 0, then this solution of this differential equation is u of x comma 0 is u naught, and the equilibrium solution is u star. So we represent this as u star with f of u star equal to 0. These are given. When you say stable, the system is stable, u of x star comma t close to u star. When you perturb a solution, then when t tends to or when large or very large t, this u of x comma t close to u star, the equilibrium solution, the system is stable. U of x comma t tends to u star, equilibrium solution u star. When t tends to infinity, it is asymptotically stable. Initially, the solution profile is bigger than the given the u star equilibrium solution. Then slowly, when time tends to infinity, these both decays and joins together. Then it's asymptotically stable. Then we come to the linear stability idea. We have initial value u of x comma 0 equal to u star plus v of x comma 0. This v of x comma 0 is the perturbation. So we have the profile u star equilibrium solution, and you are disturbing with this temporal distance or some profile. It's a force. Then you can write when t greater than 0, u of x comma t equal to u star plus v of x comma t. If you bring this v of x comma t to the left hand side, then v of x comma t equal to u of x comma t minus u star. If we substitute this this u of x comma t in the nonlinear partial differential equation ut equal to f of u, you will get vt equal to f prime of u star v. V is v of x comma t. Here it's given v is v of x comma t. Then when v of x comma t stays close to 0 for t greater than or equal to 0, then the system is stable. V of x comma t tends to 0 as t tends to infinity, the system is asymptotically stable. It's similar to nonlinear stability, but that's a bit different from linear stability. So now we are coming to the spectral stability. The eigenvalues are of we have a linear operator f prime of u star. So f prime of u star is taken from here. Linearized problem is vt equal to f prime of u v. So we are going to talk about or analyze about this eigenvalues of this f prime of u star. So we call or we represent spectrum of linear operator f prime of u star is spec f prime of u star. Then if this f prime of u star, this is stable, then if you are talking about stable in terms of eigenvalue, eigenvalues, all real part of eigenvalues in C, capital C, or complex plane, but a real part of lambda are less than or equal to 0, then it's stable. If you say neutrally stable, then some of the eigenvalues on the imaginary plane, then it's called neutral stable. So here is an important point. Spectral stability is not necessary for linear and nonlinear stability. So it's a kind of low level setup. Then spectral stability is not equal to linear because some values are in the complex plane or IR or imaginary axis. Linear stability does not imply nonlinear stability. So how to find or analyze, study stabilities? For nonlinear stability, there are many different methods available in the literature. For linear stability, there is a semi-group theory available, and for spectral stability for linear operators and dynamical system also used to analyze spectral stability. These are the methods to analyze spectral stability, linear and nonlinear stabilities of a system. Then we know when it is stable or unstable. Then if it is unstable, what kind of instabilities are there? So here perturbation means we say this b of x comma t. Then again you can combine this x and t in a single variable xi. Xi is x minus ct. If you say a system is absolute instability, it means perturbation grows at every point. So when time 0, the profile or the perturbation is this green color curve. When time grows, then perturbation grows at every point of the domain. It occupies the whole domain, a given domain. Then it's called absolute instability. So the first figure shows is an example for absolute instability. Then perturbation grows and transported to infinity. Here, infinity means either plus infinity or minus infinity, but not both. That is called convective instability. The figure second is an example. So the initial profile is solution is green curve. Then when time grows, so it's transported to the left infinity, minus infinity. So this is an example for convective instability. The third figure also an example. So if you say, so it's also transported to, you can say if you split this, it's left and right as well. Then transient instability. The unstable mode travels left or right, but not both. So then the example is the second one. So it's going to the left. So I think, sorry for this wrong interpretation. So convective instability is, it grows, it is not fixed either plus infinity or minus infinity. So it just grows and transported to infinity. It can be both as well. But in transient, the perturbation grows and it travels to left or right, but not both. That's the example, the idea for transient. So in the second figure, it's traveling, the initial profile, green profile is growing and traveling to the left infinity. But this is not, the third figure is not a example for transient instability. And remnant instability. Okay, Riemann instability. Riemann instability means instability can travel both sides. So then this is an example. The third figure is an example for Riemann instability. Then we will move to the problem setup. So how we will find the spectral values for this kind of problems. So the given differential equation in this case, u of x comma t or ut, you can write ut. I like to show the values, spatial and temporal variable here. That's why I written this x and t here. So u of ut equal to f of u, and u is in Rn. Then u star is a equilibrium solution. It's known solution. It's given, and if we linearize this nonlinear given nonlinear PDE about this u star using Taylor's series, then the linearized PDE is v of xi comma t is equal to f prime of u star v. This is the linearized PDE. Now here we have xi is a variable and t is a temporal variable. In xi itself you have x and t. Then you assume for eigenvalue problem, we always assume the solution is of this type. V of xi comma t is equal to e power lambda t v of xi, where lambda is an eigenvalue and v of xi is an eigen function in this case. Then if you substitute this in this linearized PDE, we will get this linearized eigenvalue problem LV equal to lambda v equal to f prime of u v. So lambda in complex plane. Then this implies you can write, this is nothing but a minus lambda I. So you are bringing this lambda v of xi right hand side, then f prime of u minus lambda, then you can write, make a bracket and write v of xi. So a minus lambda I xi, v of xi. So a minus lambda I, here f prime of u minus lambda I is, here we represent a of xi comma lambda, and v of xi, it may be more than one v of xi, so it's a vector function. If you have higher order differential equation, ordinary differential equation, in this case you can write a system of first order equations. So you can write this whole system linearized eigenvalue problem as v prime of xi equal to a of xi comma lambda v of xi. V is again a vector function. This is, I think, it's relevant from functional analysis. Yeah, you can find it from books. So then how to find continuous eigenvalues? So we have this problem, lambda v equal to f prime of u v of xi. If you substitute limit xi tends to plus or minus infinity here at f prime of u, this gives f prime of plus and minus. When xi tends to plus infinity, this is f prime of plus. When xi tends to minus infinity, f prime of minus. So we will use this during continuous eigenvalue calculation. So now take v of xi is e power I lambda xi, I tau xi. So tau is the wave number. Then if you substitute this function, it's nothing but cos lambda xi plus I sin lambda, tau xi. Sorry, tau xi, cos tau xi plus I sin tau xi. So then if you substitute this in the eigenvalue problem or the first line of this slide, then you will get lambda I plus or minus of tau equal to f prime plus or minus. Here I varies based on the dimension of the A or system, order of A or dimension of this given system, or order of the differential equation. So these lambda I plus or minus tau are finite number of algebraic curves in complex plane C. Suppose if we take these finite number of curves, or K represents the union of regions inside these finite number of curves, then the continuous of the spectrum of the linear operator. This is when xi tends to infinity plus or minus infinity case, but the original operator is this linear operator is contained, the continuous spectrum of that linear operator contains in the union of these curves lambda I plus or minus. I is the dimension of the system. And so this is about how to find continuous spectrum. Then so how to find discrete spectrum. So in this kind of problems, you have continuous spectrum as well as discrete spectrums. So we know now how to find continuous spectrum. Then we are now in the how to find in the discrete eigenvalues. I think you people are doing for constant matrix are mostly discrete eigenvalues. Those are discrete for discrete eigenvalues. So here the given differential equation is the perturbed differential equation is the system is V prime of xi equal to A xi lambda V xi. When xi tends to plus infinity, then this system A of xi comma lambda becomes A plus. A plus is a constant matrix, but A of xi comma lambda is not a constant matrix. It's an operator matrix. It contains differentials as well as equilibrium solutions. So it's not easy to find eigenvalues for this A of xi comma lambda. But A plus or minus, when xi tends to plus or minus infinity, this A of xi comma lambda becomes A plus or A minus. These are just representation, A plus or A minus. So when xi tends to plus infinity, this A xi comma lambda is A plus. So that's a constant matrix. When xi tends to minus infinity, A xi comma lambda equal to A minus is a constant matrix. Then it's easy to find the eigenvalues. There's a discrete eigenvalues. So spectrum of A plus is mu I plus. Spectrum of A minus is mu I minus. So this I, where is the order of the differential equation, or 1, 2, or dimension of the differential equation, or dimension of the system, or order of the differential equation. Then eigenvectors of A plus or A minus is Pi plus or Pi minus. So I also varies from 1 to n. Now you know this mu I plus minus or Pi plus minus are constant eigenvalues and constant eigenvectors. So take this eigenvector, a constant eigenvector as an initial value, and this you can form an so from this eigenvector and eigenvalues you can construct a function that is the solution for the linear operator. So we take now A minus, when xi tends to infinite minus infinity, A xi comma lambda is equal to A minus. We take A minus matrix and see what are the positive eigenvalues with the positive real part of mu I minus. You choose those eigenvalues and the corresponding eigenvectors we call Pi minus of A minus. You assume this Pi minus for initial value for the solution Vi minus of xi, then and assume the spatial domain minus L to xi with a large L, with a large distance L, and numerically construct the solution, and that is V1 minus. Similarly, you can find, suppose you have k eigenvalues with a positive real part, then you have k solutions V1, V2, V3, V etc. Vk minus of xi. These are for left decaying solutions. Similarly, you can choose you choose A plus, and from A plus you can see eigenvalues with a negative real part, that we represent mu j plus, and choose those corresponding eigen vectors pj plus of a plus. Then construct solution vj plus of psi with a given initial value pj plus of psi from xi to L. Then now we have vi minus of xi I equal to 1 to k, vj plus of xi j k plus 1 to n. These are linearly dependent. If you have two vectors linearly dependent, the Wronskian becomes 0. So the Evans function here we call is nothing but Wronskian of the decaying solution in both equilibrium states. So Evans function is d of lambda, we represent here, d of lambda equal to determinant of, so left decaying solutions are v1 minus of xi, etc., vk minus of xi. Then the right decaying solutions from k plus 1 to n, vk plus 1 of xi, etc., vn plus of xi. So point spectrum of a of xi comma lambda is the zeros of the Evans function at some point psi. You can match any, you can take any psi, that doesn't matter for this. So this is the procedure to find discrete eigenvalues. So now if you have a nonlinear PD, if you want to find eigenvalues, you need to find discrete as well as continuous eigenvalues. So I think you're now clear about this too. Then we will go to some, like these are procedures for how to find this left decaying, right decaying solution using some numerical method, numerical scheme. So in my case, I used this Lee midpoint and Magnus method. So from literature, they said it's effective during for linear or for linear like matrix or linear differential equation computation, solution computation. So I use Lee midpoint and Magnus method. So then I'm coming to the example for this technique or this idea. So this equation is called Allen-Kahn equation. So this is nothing but ut, left side is a derivative with respect to t, first order derivative. Then right side is second order spatial derivative. Then d is a diffusion coefficient plus there is a forcing function f of there is a function f of u of x comma t. So here I chosen the f of u comma u of x comma t is, or f of u is equal to u minus u cube. It's a bistable. If you plot this, you have two equilibriums, so that's why it's called bistable. When so f of u vanishes at h minus, h naught, and h plus, so it becomes 0 at these points. We are talking only about this reaction term f of u. And between h minus and h plus, the behavior is like this. So h minus less than h naught less than h plus. So we can use some techniques like Jacobi elliptic or some other techniques to find solution for this differential equation. So if you use some techniques, so you will get these kind of solutions. So u1 of xi, so there are 6 solutions. u1 of xi is again x minus ct. u1 of xi is plus c2 minus c1 e power root 2 xi by denominator, and psi is here x. So here this is example for stationary wave solution. Here c is 0 and u2 is minus, so the minus and remaining term is same. So if you plot this xi versus u of xi, then you will get these profiles. u1 is the u1 is the first curve, the from starting from 1 to ending at -1, and the other one is starting at -1 and ending at +1. and U3 are U3, U4, U5, U6 are traveling waves. And here in this U3, xi is equal to x plus 3 by root 2t. So C is this term, x minus ct is the is I. So then C is so this minus 3 by root 2t. So that represents this figure, or this is the pictorial representation of this U3. So similarly, you can plot other solutions. Then if you substitute e power I lambda xi in the linear operator, so then you have to perturb this differential equation, Allen-Cullen equation, depend on this each, based on these each solutions. So you will have 6 differential equations, perturbed differential equations. So those, each one will give you lambda 1, 2, 3, 4, 5, 6. These are continuous spectrums for this differential equation. And here, continuous spectrum of U1 and U2 of xi, we represent lambda 1, comma 2 plus or minus psi. So this plus or minus psi is again depend on limiting value of u of xi. Limit xi tends to plus infinity. This is lambda plus 1. 1 means corresponding to the u1 of xi. So these are all are equal to minus tau square minus 2. For other cases, if you take this, if you do the same way, you will get when xi tends to minus infinity and xi tends to plus infinity, like this. You can plot these solutions. So this in the complex plane, real value, real versus complex, then this makes these plots. So U3, comma 5 of xi. So this for this solution, we have the continuous spectrum lambda 3, comma 5 of tau. So the pictorial representation of these two are here in the first figure. Then we'll move to discrete spectrum. Take U1 of xi or U2 of xi, because these two, if you see this continuous spectrum, these are unstable solution, because it's crossing